Okay, welcome to the second video in my series on wild networking. This is for network engineering that you would see out in the wild as opposed to on a certification test. In the last video, we read an article written for a software developer to understand what happens when you enter a URL into the browser. This article focused a lot on higher layers in the OSI model, such as the session, presentation, and application layer. So in addition to that, there's of course the lower layers, but those are the layers that I'm a lot more familiar with. So in this video, we're going to take another dive into those protocols that were mentioned in the blog. You can see I'm keeping my own notes here, and from the blog we learned about DNS and HTTP mostly. But I would like to dive in a little bit deeper and learn especially some designs and trade-offs associated with each of those. In addition to that, in this video, now I've got to keep it an hour or shorter, but I would like to get into ARP scaling especially and learn about that as soon as possible, and L2 topologies. So when you enter a URL into a browser, yes, you have DNS, yes, you have HTTP transfers, but you also have this whole networking component which was left out of the blog post. So we're going to start with the DNS component that was in the blog post, but then we'll go right into the networking component, and we'll even talk, I think, about BGP when it comes to this second step as well. So that'll push the HTTP back farther, but I think that's okay because I am, for the most part, comfortable with the idea that there's HTTP gets, HTTP posts, that there's XML, YAML, Yang, and that there's cookies with keys. Just the fact that inside Chrome there is this just perfectly designed tool here to teach you how all of this works, where you can even go ahead and capture the traffic that's being sent here, see all of the request headers, the response headers, and even go as far as to craft your own custom headers by using this fetch code. There's just enough there where, and yes, this is a series focusing on network engineering as is relevant in the real world and not in the test, so this is probably going to be your main tool if you're doing this in the real world, because we all have a browser, and this is available in every browser. If I pull up Edge, which I've got in my extension, in my toolbar there still, you can hit F12 in Edge as well, and Edge has its own version of that. So sometimes if you're in the real world working for an employer, they'll, if they're really cruel, disable this. So if you are at a tech job where you're expected to focus on tech and you see this is disabled, I would talk to your manager or submit a ticket or something and try to get this enabled, because real world development and networking is really this tool is, I think, a great tool for doing that. I have used this tool many times in the real world, and it has allowed me to do things I could not have done without having access to this tool. So okay, so let's go ahead and continue on to the next part. So the next part will be reading the Wikipedia article on DNS, and then the Cloudflare article, and then we're going to be explaining some designs and trade-offs, specifically the round-robin, load balancer, geographic, and anycast designs and trade-offs. Now, I already know what those are. DNS kind of has a problem, and that's that you need to, so DNS is the phone book of the internet. It's how you are able to, when I call somebody on my phone, I've got to memorize their number, 555, 26, 309, whatever that number is. That's what we're talking about. We're talking about the actual numbers. So we could very easily be in that same situation when it comes to the internet. Instead of saying just Google it, we could very easily be in a situation where we say just 8.8.8.8 it. And obviously that would not be that great of a situation. And not only that, 8.8.8.8 wouldn't even probably get you to the page of Google where you could search for results. That would be like 172.178.163.94. So already you can see there's a very clear need to have that plain text name for those kinds of addresses. And when you have a phone, you don't need that, because you can say, oh, well, Jim's number is 555-232, whatever it happens to be. But you used to get an actual physical phone book, and with just how many websites there are, all that's just not practical. The phone book has to be built into the technology, and that's what DNS is. Okay, so this is a pretty long article, but it's got some good things about best practices in here. It's got some good things about security standards. So we're going to go and read this whole article. I don't think it'll take too long, maybe 15 minutes, but let's get a timer on this. And then we'll just start reading this and see how long it takes. The domain name system, DNS, is a hierarchical and decentralized naming system for computers, services, and other resources connecting to the internet or a private network. And these are two important concepts in network engineering to understand: the difference between a decentralized and a centralized architecture. And it looks like this is something else that is important as well, but I don't immediately recognize this as is relevant to network engineering. So this will be a good one to look into. This will be a good one to review. It associates various information with domain names assigned to each of the participating entities. Most prominently, it translates more readily memorized domain names into numerical IP addresses needed for locating and identifying computer services and devices with the underlying network protocols. By providing a worldwide distributed directory service, the domain name system has been an essential component of the functionality of the internet since 1985. And unfortunately, this is where a lot of the challenges with network engineering come into play, in my opinion, for new network engineers. They'll say, why can't I, get my network to work? I'm trying to SSH into admin at router 1 and it's not working. Well, where is it getting DNS, and is it mapped to the name in that location? So brand new network engineers, day one in network school, oftentimes don't really focus on DNS, I would say. It's more, you learn the number schemes, and then DNS is kind of, in my opinion, has been a bit more of kind of an afterthought in some ways, because it's you don't, when you look at a routing table, when you look at routing protocols, you don't have DNS name resolutions in that case. So most of network engineering DNS resolutions. So if I would open this here, and then I would go to network, and then I would look at here, you'd see the remote address is not resolved in DNS. It gives you the actual number IPs. So it's really important, real world, in the wild, to know what these, to be comfortable with the actual number IPs. Yes, you're going to need to know what DNS does, how it does it, and how to design it to do it well. But real world network engineering, as opposed to software, as opposed to like software development or something like that, I would say focuses more on actual numbering for the IPs, instead of like the actual like distributed directory service or the actual DNS records. That would be more a sysadmin instead of a network engineer. There's kind of a distinction between the two, sysadmin and network engineer, and in my opinion, that's kind of where the distinction lies. Sysadmin would be managing those mappings of the DNS records to the IPs and kind of what the names are, and a network engineer would be focusing just on the IPs and making sure that the management, that the networking gear is configured correctly with those IPs, and that it's designed to use an appropriate set of IPs. So it looks like my camera stopped working and I'm just frozen on the screen there. So I'm gonna click deactivate on my camera and then activate. There we go, and it's back. The domain name system delegates the responsibility of assigning domain names and mapping those names to internet resources by designing authoritative name services for each domain. Network administrators may delegate authority over subdomains of their allocated namespace to other name servers. The mechanism provides distributed and fault-tolerant service and was designed to avoid a single large central database. The domain name system also specifies the technical functionality of the database service that is at its core. It defines the DNS protocol, a detailed specification of the data structures and data communication exchanges used in DNS as part of the Internet Protocol Suite. The Internet maintains two principal namespaces, the domain name hierarchy and the Internet Protocol IP address spaces. The domain name system maintains the domain name hierarchy and provides translation services between it and the address spaces. Internet name servers and a communication protocol implement the domain name system we'll just keep opening all of these. It'll fill up everything, but we'll go through, and if anything is of note, in my opinion, I will bring it up. Remembering that this is focusing on real-world networking as you see it in the wild, so if there's any concept that is not immediately applicable to a real-world need-to-know situation, that I will not be focusing on that as much. For instance, Xmpp, I've never heard of that, so yeah, it's like a specific protocol for a specific kind of instant messaging. We'll be focusing more on like how to choose which kind of protocol to use in your design and why. That would be a real world thing that you would likely need to do if you were hired for any network engineering task to design some sort of network that, or some sort of system that meets a set of objectives. A DNS name server is a server that stores the DNS records for a domain. A DNS name server responds with questions to queries against this database. The most common types of records stored in the DNS database are for start of authority, SOA, IP addresses, A and quadruple A, SMTP mail exchangers, MX, name servers, NS, pointers for reverse DNS lookups, PTR, and domain name aliases, CNAME. Although not intended to be a general purpose database, DNS has been expanded over time to store records for other types of data for either automatic lookups such as DNS SEC records, or for human queries such as responsible person RP records. As a general purpose database, the DNS has also been used in combating unsolicited email spam by storing a real-time black hole list, RBL. The DNS database is traditionally stored in a structured text file in the zone file, but other database systems are common. Okay, so, as I said, I want to focus on it in the wild, in the real world as you would see it. So the history of it, I think is important. But I think that would be another series, would be the history of networking. So something like that wouldn't necessarily belong in this series. But the function, I think that's really important. The structure, of course, that's important. Operation, that's probably the most important. But I think I said I wanted to just read the whole thing and see how long that took me. So let's try that. Right now I'm only at 10 minutes anyways. Function. An often used analogy to explain the domain name system is that it serves as the phone book for the internet by translating human-friendly computer host names into IP addresses. For example, the domain name www.example.com translates to the address 93.184.216.34, which is an IPv4 address. And it also has an IPv6 address, which is 128 bits, so represented in hexadecimal. So this is a lot to read. You can see it here. The DNS can be quickly and transparently updated, allowing a service's location on the network to change without affecting the end users who continue to use the same hostname. Yeah, and that's another thing too, and I'll explain that more after I finish this paragraph. Users take advantage of this when they use meaningful uniform resource locators, URLs, and email addresses without having to know how the computer actually locates the services. So I'm going to bring out my sketchpad here, and I will explain what this second sentence here means. The DNS can be quickly and transparently updated, allowing a service's location on the network to change without affecting the end users who continue to use the same host name. So to some people that might be self-explanatory, but I will just be very clear about what that means. So I've got a sketchpad here. It's a there we go, Sketch Together. This is my favorite app to use because it's free. You only get to use it for an hour, but that's often the only amount of time I need. Okay, and then all right. All right, so I've got my sketchpad up here that I think will be able to explain everything. There we go. So what that means is if I here were a user sitting at a computer, so this is me on the computer, and I wanted to access a resource here, so we'll make a rack with blade servers in it, and I wanted to go to this one, which we'll just call we'll call it 96.64.100.1. So I'm going out to that address. Now let's say that this person here who manages this system, there's some sort of issue with this 96.64.100.1, so they need to take it out. But in the meantime, they have this 96.64.100.2 that I can still do whatever I needed to do on .1. I can just do that on .2 while .1 is being repaired, and then it's going to be added back at .1. So if I needed to know to go to 96.64.100.1 and they needed to have me use .2, they would have to tell me to use the new .2, and you can imagine how much coordination and effort that would take. Another way to say it is, let's say that I have a phone number, and I've actually been through this, and my phone number is 555.555.5555, but then something happens with my phone, my carrier or something, and I got a new number, 5556. So now everyone's going to be trying to call me at 5555, and they're not going to call me at the right number unless they know that I changed my number to 5556. So imagine if instead of trying to call me at my phone number, they called me at my name, and then what happened when you called was you would seamlessly behind the scenes first be calling some agency that has my name mapped to a number, and that I can say, okay, well, this is my number, 5555, but if anything happens where this number is unreachable or something like that, give me a try at 5556. So I can do that now by just calling a friend or whoever wants to call me and say, hey, I've actually got two numbers now. There might be a problem with my first number. If there is, go ahead and call my second number. Or what would be really nice and what the internet does is have, instead of calling my friend in a decentralized manner, and then here we're getting into centralization versus decentralization. So I thought this would be, I'm surprised that it's decentralized. I thought it was centralized. Okay. Huh. All right. Well, it's but as I'm talking about the other example, imagine if I could, instead of telling my friend, hey, I've got two numbers because I think something's going to happen with the first one, please try the second one if there's a problem. Or you can think of on like a job application, they ask you for your work number, for your home number, for multiple numbers in case they can't reach you at one of the numbers, they'll try another one. So what if instead of that, they just dialed your name, and then in doing that, it reached out to a location that had your numbers on it. So instead of a job application listing all of your numbers with the phone company or whoever, you would just say, here's my name, here's my numbers, and then what would happen is they would call your name instead of your numbers, and it would automatically use the number that is able to ring and able to reach you. So if there's a problem with one of your numbers, you no longer need to reach out and make sure people have your correct number. You just need to go to a place where your information is stored and add the new number, remove the old number, and you can have multiple numbers, and if something is wrong with one of their numbers, or you're just receiving too many calls on this phone, you want some calls on this phone as well, you can do that. So yeah. So here, instead of having to inform this user .to, this user now goes to google.com, which can belong to any of these addresses. So where they would have been going to .1 automatically through the DNS resolution, now that this is offline, they're now going to .2. An important and ubiquitous function of the DNS is its central role in distributed internet services such as cloud services and content delivery networks. When a user accesses a distributed internet service using a URL, the domain name of the URL is translated to the IP address of a server that is proximal probably. This one I actually don't know. Proximal.
Proximal.
Yeah, it's proximal to the user, and this is ubiquitous.
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 Ubiquitous. Ubiquitous.
Okay, that one's ubiquitous. Okay, but anyways, the key functionality of the DNS exploited here is that different users can simultaneously receive different translations for the same domain name. A key point of divergence from a traditional phone book view of the DNS. Yep, and I explained that before. You would look at the phone book, you say Jim Jones is at this number, don't drink his Kool-Aid. But with the internet, you can say, call Jim Jones. I don't even know what his number is. We'll look it up. Oh, that number's not ringing. will try this other number automatically. That number, for some unknown reason, all of his numbers are no longer working. You have the opportunity to try each of the numbers automatically instead of having to try each one and hope that one works. You automatically get the one that is going to work. So the key functionality of the DNS exploited here is that different users can simultaneously receive different translations for the same domain name. A key point of divergence from the traditional phone book view of the DNS. This process of using the DNS to assign proximal servers to users is key to providing faster and more reliable responses on the internet and is widely used by most major internet services. The DNS reflects the structure of administrative responsibility in the internet. Each subdomain is a zone of administrative autonomy delegated to a manager. For zones operated by a registry, administrative information is often complemented by the registry's RDAP, RDAP, and WHOIS services. That data can be used to gain insight on and track responsibility for a given host on the network. Yeah, so used this before. The WHOIS, oops, oh yeah, here it is. So you can see basically that phone book entry that lists the name as long as with the numbers. Okay, so the history of DNS, using a simpler, more memorable name in place of a host's numerical address dates back to the ARPANET era. A Stanford Research Institute, or the Stanford Research Institute, I guess there's only one, now SRI International, maintained a text file named hosts.txt that mapped host names to the numerical addresses of computers on the ARPANET. Elizabeth Feinler developed and maintained the first ARPANET directory. Maintenance of numerical addresses, called the assigned numbers list, was handled by John Postel at the University of Southern California's Information Sciences Institute, ISI, whose team worked closely with SRI. And this is what's really cool about learning about the internet history. And it's a lot different if you learn about, for instance, the history of the automobile. You're talking about like Henry Ford from like 1910, you know, more than 100 years ago. Completely different ball game. It's basically you're reading archives, which can be interesting, but I yeah, okay. But I think it's a bit more interesting. A living history. That's what I'm saying, is that the history of the internet is a living history. You can see she is 90 years old, currently alive, born in 1931. This is a really important person who basically invented this system of DNS. She's still alive, 90 years old. You can probably even see a video of her talking about her job to do that. Yeah, so there's an Internet Hall of Fame. Yeah, and here she is talking about why she's in the Hall of Fame. So yeah, it's a living history. So it's really fascinating to look into the history of the internet, because it's going to be, because it's currently in the making right now. Addresses were assigned manually. Computers, including their host names and addresses, were added to the primary file by contacting the SRI's Network Information Center, NIC, directed by Elizabeth Feinler by telephone during business hours. Later, Feinler set up a WHOIS directory on a server in the NIC, Network Interface Card, for retrieval of information about resources, contacts, and entities. She and her team developed the concept of domains. Fendler suggested that domains should be based on the location of the physical address of the computer. Computers at educational institutions would have the domain edu, for example. She and her team managed the host naming registry from 1972 to 1989. By the early 1980s, maintaining a single centralized host table had become slow and unwieldy, and the emerging network required an automated naming system to address technical and personnel issues. Postel directed the task of forging a compromise between 5 competing proposals of solutions to Paul Makapetris. Makapetris instead created the domain name system in 1983. The Internet Engineering Task Force published the original specifications in RFC 882 and RFC 883 in November 1983. In 1984, 4 UC Berkeley students, Douglas Terry, Mark Painter, David Riggle, and Sunan Su, wrote the first Unix name server implementation for the Berkeley Internet Name Domain, commonly referred to as BIND, B-I-N-D. In 1985, Kevin Dunlap of DEC substantially revised the DNS implementation. Mike Carrells, Paul Almquist, and Paul Vaxi have maintained BIND since then. In the early 1990s, BIND was ported to the Windows NT platform. In November 1987, RFC 1034 and RFC 1035 superseded the 1983 DNS specifications. Several additional requests for comments have proposed extensions to the core DNS protocols. The structure of DNS, domain namespace. The domain namespace consists of a tree data structure. Each node or leaf in the tree has a label and 0 or more resource records, RR, which hold information associated with the domain name. The domain name itself consists of the label concatenated with the name of its parent node on the right, separated by a dot. The tree subdivides into zones beginning at the root zone. A DNS zone may consist of only one domain or may consist of many domains and subdomains, depending on the administrative choices of the zone manager. DNS can also be partitioned according to class, where the separate classes can be thought of as an array of parallel namespace trees. Administrative responsibility for any zone may be divided by creating additional zones. Authority over the new zone is said to be delegated to a designated name server. The parent zone ceases to be authoritative for the new zone. So we can see that here. We've got, looks like these zones, yep, so zone of authority managed by a particular name server. And we've got the resource records associated with the name. Okay. Domain name syntax, internationalization. The definitive descriptions of the rules for forming domain names appear in RFC 1035, RFC 1123, RFC 2181, and RFC 5892. A domain name consists of one or more parts, technically called labels, that are conveniently concatenated and delimited by dots, such as example.com. The rightmost label conveys the top level domain. For example, the domain name www.example.com belongs to the top level domain com. The hierarchy of domains descends from left to right. Each label to the left specifies a subdivision or subdomain of the domain to the right. For example, the label example specifies a domain of the com domain, and www is a subdomain of example.com. This tree of subdivisions may have up to 127 levels. A label may contain 0 to 63 characters. The null label of length 0 is reserved for the root zone. The full domain name may not exceed the length of 253 characters in its textual representation. In the internal binary representation of the DNS, the maximum length requires 255 octets of storage, as it also stores the length of the name. Although no technical limitation exists to use any character in domain name labels which are representable by an octet, host names use a preferred format and character set. The characters allowed in labels are a subset of the ASCII character set, consisting of characters A through Z, capital A through capital Z, digits A0 through 9, and hyphen. This rule is known as the LHD rule, letters, digits, hyphen. Domain names are interpreted in case-independent manner. Labels may not start or end with a hyphen. An additional rule requires that top-level domain names should not be all numeric. But those are just, looks like those are just like not real rules, so you can do like special characters. Oh, it's going to be, is there a site? Okay, well, never mind. It looks like it is more of a hard and fast rule. The limited set of ASCII characters permitted in the DNS prevented the representation of names and words of many languages in their native alphabets or scripts. To make this possible, ICANN approved the Internationalizing Domain Names in Applications (IDNA) system, by which user applications such as web browsers map Unicode strings into the valid DNS character set Punycode. In 2009, ICANN approved the installation of internationalized domain name country code top-level domains, CCTLDF. In addition, many registries of the existing top-level domain names, TLDS, have adopted the IDNA system, guided by RFC, and these are, these are new RFCs. I was going to say these are the classic RFCs we've seen time and time again, but it looks, okay, please stop. Alright, it's charging. Okay, so so in these RFCs here, we're not going to look at them specifically. So name servers. The domain name system is maintained by a distributed database system which uses the client-server model. The nodes of this database are the name servers. Each domain has at least one authoritative DNS server that publishes information about that domain and the name servers of any domains subordinate to it. The top of the hierarchy is served by the root name servers, the servers to query when looking up, resolving a TLD. Authoritative name server. An authoritative name server is a name server that only gives answers to DNS queries from data that has been configured by an original source, for example, the domain administrator, or by DNS methods, in contrast to answers obtained via a query to another name server that only maintains a cache of data. An authoritative named server can either be a primary server or a secondary server. Historically, the terms master/slave and primary/secondary were sometimes used interchangeably, but the current practice is to use the latter form, primary/secondary. A primary server is a server that stores the original copies of all zone records. A secondary server uses a special automatic updating mechanism in the DNS protocol in communication with its primary to maintain an identical copy of the primary records. Every DNS zone must be assigned a set of authoritative named servers. This set of servers is stored in the parent domain zone with named server NS records. An authoritative server indicates its status of supplying definitive answers deemed authoritative by setting a protocol flag called the authoritative answer, a bit in its responses. This flag is reproduced prominently in the output of DNS administration query tools such as dig to indicate that the responding name server is an authority for the domain name in question. Okay, so this next section has got some problems in it. I'm really starting to question my strategy here of just reading through the whole Wikipedia article. A lot of it seems to be going over my head, but like it's not. I mean, I know about DNS. I went to networking school where we learned about it. I've troubleshooted some problems with its resolution. So to not have any of this article kind of trigger, stuff and hit home is in my mind not a sign that my knowledge base is lacking. It's that the article is off topic. But it looks like we're going to get into more on-topic things here. I gotta hard limit this video to 1 hour, so I'm not sure how far I will get. Address resolution mechanism. Domain name resolvers determine the domain name servers responsible for the domain name in question by a sequence of queries starting with the rightmost top-level domain label. For proper operation of its domain name resolver, a network host is configured with an initial cache, hints, of the known addresses of the root name servers. The hints are updated periodically by an administrator by retrieving a dataset from a reliable source. Assuming the resolver has no cached records to accelerate the process, the resolution process starts with a query to one of the root servers. In typical operation, the root servers do not answer directly, but respond with a referral to more authoritative servers. For example, a query for www.wikipedia.org is referred to as the org servers. The resolver now queries the servers referred to and iteratively repeats this process until it receives an authoritative answer. The diagram illustrates this process for the host that is named by the fully qualified domain name, www.wikipedia.org. A DNS resolver that implements the iterative approach mandated by RFC 1034. In this case, the resolver consults 3 name servers to resolve the fully qualified domain name. So yeah, once we're into reading about RFCs, it's like you can. I just don't know, because I've of course got a limited amount of time, so I've got to be concerned with that. The mechanism would place a large traffic burden on the root servers if every resolution on the internet required starting at the root. In practice, caching is used in DNS servers to offload the root servers and as a result, root name servers actually are involved in only a relatively small fraction of all requests. Recursive and caching name server. In theory, authoritative name servers are sufficient for the operation of the internet. However, with only authoritative name servers operating, every DNS query must start with recursive queries at the root zone of the domain name system, and each user system would have to implement resolver software capable of recursive operation. To improve efficiency, reduce DNS traffic across the internet, and increase performance in end-user applications, the domain name system supports DNS cache servers, which store DNS query results for a period of time determined in the configuration, the time to live, of the domain name record in question. Typically, such caching DNS servers also implement the recursive algorithm necessary to resolve a given name, starting with the DNS root through to the authoritative name servers of the queried domain. With this function implemented in the name server, user applications gain efficiency in design and operation. The combination of DNS caching and recursive functions in a name server is not mandatory. The functions can be implemented independently in servers for special purposes. Internet service providers typically provide recursive and caching name servers to their customers, for their customers. In addition, many home networking routers implement DNS caches and recursors to improve efficiency in the local network. So let's take a look at my home network DNS settings for caching. I want to be a bit careful about that because I might open myself up to security exploits if I show too much about what my home network looks like. So for now I'm doing this on the other screen, but okay. Maybe there's, okay, so yep, advanced. So it's probably going to be under advanced. Okay, I am going to show this though because the wild networking, what you see in the wild, you're definitely going to see this in the wild. So you can pull up your command prompt right now as you're watching this video. If you're on Windows, it's ipconfig, and then you're going to, probably on wireless, but whatever you're on, you can look at your default gateway and then plug that into the URL, and that will take you to your router. And you'll need to know the password to that router. For most of you watching this video, if you're new, it will be the default password. It'll probably be written on your router somewhere if you go pick it up and look at it, or if you saved the box it came in or something like that, the manual it came in, you'll see the password there. For hopefully most people watching this, you will have changed that password to something that is more secure. That's what I did. So I am logged into the router right now. You will not see this. If you do what I did, you will see a prompt for a username and password. Then you will see something like this. It depends on what you have. If you have Netgear, you'll see the logo of what you have. There's all kinds of different router manufacturers. So here I am in Basic. In Basic, there are settings for DNS, but I don't see anything for DNS caching. But this is very much real world networking as you see. Okay, so let's take a look at, first of all, I'm going to deactivate and activate my camera. Okay, so now it's back. I definitely need to buy like a I need to buy something to solve this problem of my camera stopping and starting. Alright, so advanced setup. Aha, here we go. So now we've got dynamic DNS, and we've got okay. Yeah, we've got extra DNS settings. I'm not sure if this is, I was looking for something that would be like DNS caching that they seem to be talking about, but I don't see that. Okay, so, but this, as I said, is very much something you will see and deal with in the wild, so I'm glad I pulled that up. Next is going to be so many home networking routers implement DNS caches and recursors to improve efficiency in the local network. So probably has that. If it does, perhaps you can't turn it off, so that's why there's no information about it in there. DNS resolvers, and I've got 4 minutes, so this is going to be my last record, I believe, my last part that I read. The client side of the DNS is called a DNS resolver. A resolver is responsible for initiating and sequencing the queries that ultimately lead to a full resolution, translation of the resource sought, for example, translation of a domain name into an IP address. DNS resolvers are classified by a variety of query methods such as recursive, non-recursive, and iterative. A resolution process may use a combination of these methods. In a non-recursive query, a DNS resolver queries a DNS server that provides a record either for which the server is authoritative, or it provides a partial result without querying other servers. In the case of a caching DNS resolver, the non-recursive query of its local DNS cache delivers a result and reduces the load on upstream DNS servers by caching DNS resource records for a period of time after an initial response from upstream DNS servers. In a recursive query, a DNS resolver queries a single DNS server, which may in turn query other DNS servers on behalf of the requester. For example, a simple stub resolver running on a home router typically makes a recursive query to the DNS server run by the user's ISP. A recursive query is one for which the DNS server answers the query completely by querying other name servers as needed. In typical operation, a client issues a recursive query to a caching recursive DNS server, which subsequently issues non-recursive queries to determine the answer and send a single answer back to the client. The resolver or another DNS server acting recursively on behalf of the resolver negotiates use of recursive service using bits in the query headers. DNS servers are not required to support recursive queries. The iterative query procedure is a process in which a DNS resolver queries a chain of one or more DNS servers. Each server refers the client to the next server in the chain until the current server can fully resolve the request. For example, a possible resolution of www.example.com would query a global root server and then a com server, and finally an example.com server. Okay, so this is the 1 hour mark. Got about 15 seconds until I get there. So unfortunately, I think this is the best I can. This is all I can do for this video. I think there's a way to. Yeah, like can't you use like? I thought there was a way you could. No, let's see here. How do you? Is there maybe the @ symbol? I thought there was a way you could like come back to what you had, where you have left off on a page. URL to come back to where you left off on a website. Wikipedia. Yeah. Yeah, so you can have a section link. Yeah, I thought it was a. Yeah, I thought you could use the. Oh, but you need to know what it's at. Okay, I think you need to fill in the spaces with underscores. So yeah, I can save where I left off by yeah, pasting this in here and then replacing these with underscores. Like that. Yeah, there we go. Okay, so now if I save this here, okay, so I'm actually gonna be honest here. I'm really dissatisfied with how I spent the last hour. I just don't think a lot of what I did is relevant to the real world in a lot of ways. So I'm gonna, between videos here, think about how I can be a bit more effective in how I'm using my time here for this series. Let me know in the comments if there's something that you've seen in the real world that you want me to dive into and talk about, or some sort of design consideration you're thinking about. I definitely am going to be, I think, changing a lot about how I create the next video based on what I did in this video. Alright, but until then, thanks for watching this video, and I'll see you in the next one.